Hello everyone, the next chapter we're going to talk about is chemical thermodynamics. This first video, I'm going to try to keep it a little bit short since technically you should be watching this the same day you've taken the exam. And so what I want this to serve as is just sort of an intro to thermodynamics. And then next week we can get into more of the math part of thermo and we can talk about some of the finer details. But for now, let's just talk about some general thermo concepts and how they apply back to what we've been learning. So the first thing we want to talk about is just types of reactions. So we've looked at some of these, but let's look at them a little bit closer, and then we'll talk about how that relates to what we're talking about now. Okay, so the first type of reaction we can talk about, we have reactions where we represent with a forward arrow only. Okay, and we know that this type of reactions, we're trying to say that they proceed completely in the forward direction. Okay, and if we put that in terms of our equilibrium constant, we would say that KEQ is much, much greater than 1. Okay, so that tells us that this reaction lies completely in the forward direction. So here we have a combustion reaction where we have methane reacting with oxygen to give us CO2 and water. And so with this type of reaction, basically all of your fuel is going to be burned up. So we know that basically it's going to lie completely towards the product side. And hopefully if everything's done right, we'll have no reactant left over. Okay, another type of reaction we could look at is a reaction that doesn't proceed at all. Okay, so in this case, we would have a KEQ much, much less than 1. Okay, in other words, meaning that it doesn't lie in the forward direction whatsoever. Okay, so this example of this would be something like gold metal, so solid gold, reacting with oxygen. Okay, in this case, we would draw an arrow with an X through it, meaning that we don't have a reaction. And we could write NR, just to let us know that indeed no reaction is occurring with this. Okay, the other type, and this is what we just talked about, are equilibrium reactions. So here we have nitrogen reacting with hydrogen to give us ammonia, okay, the Haber-Bosch process. Okay, notice we have equilibrium arrows. Okay, so we know that this reaction can be driven either in the forward direction or in the reverse direction. Okay, so we have a K equal to 1.45 times 10 to the minus 5, so not much, much greater than 1 and not much, much less than 1. Okay, so we know that we have some equilibrium here. Okay, so what we want to talk about now is how do we determine these key values, so our equilibrium constants. In the last couple of chapters, we talked about how to calculate them, but not so much about what determines them. So what are we going to talk about? What we're going to talk about now is what actually determines these KEQ values. So the first thing we're going to start out with here is just some definitions. Okay, so first one, thermodynamics. What is thermodynamics? Thermodynamics is just the study of energy and its transformations. Okay, so that's just your basic definition. Two more things we need to know here. Kinetic energy, represented as Ke. This is the energy of motion. Okay, so just like in physics, we define it as Ke, kinetic energy, is equal to 1/2 mass times velocity squared. So that should be the same as your physics definition. Okay, then we have potential energy, which is represented as Pe. So this is stored energy. So we can represent it in terms of charge. So we could say potential energy is equal to some constant times Q, or Q times Q1 times Q2 over the distance of those two charges. Or we could put it in terms of height and gravity. So we could say that potential energy is equal to mass times height times the gravitational force. Okay, and we'll talk about more about what these mean in terms of chemistry. Okay, but just understand these are the definitions that we're coming from. So you have thermodynamics is just the study of energy and its transformation. Then we have both kinetic and potential energy, where kinetic is energy of motion, potential energy is stored energy. Okay, and we're going to talk about the fact that matter possesses both energy as both kinetic and as potential energy sometimes. Okay, so we're going to talk about things like the universe. Okay, so we have to kind of get these definitions down first. So when we're talking about the universe is going to be equal to the system plus the surroundings. Okay, so the system is generally what you're talking about. So it might be, a beaker, or it could be a calorimeter, something like that. That's going to represent your system. Everything that's not the system will be your surroundings. Okay, and we'll talk about different versions of this, but just remember, if we're studying it, that's probably going to be the system. If it's everything else, that's your surroundings. So for instance, if you were to maybe heat up a beaker of water and take its temperature, you would be measuring the temperature of the system. Everything surrounding that beaker in the lab, that would be the surroundings. Okay, and then everything outside of that would be the universe. So both the system and the surroundings are both inside of the universe. So they both make up the universe. Okay, and so we can also talk about things like internal energy. So the internal energy is kind of similar to the universe. Okay, the internal energy is the sum of the sum total of the kinetic and the potential energy of the system. Okay, so that's how much energy is inside of the system, both kinetic and potential. Okay, a chemical or physical change that occurs to the system must lead to a change in its internal energy. So we can say delta E here, and we'll get to what E is briefly. Okay, so we're going to say delta E is equal to E final minus E initial. Okay, notice this is a state function, so all we care about is where do we end and where do we come from. Okay, and that's going to be also equal to the energy of the products minus the energy of the reactants. So again, where do we come from and where do we end up? Okay, so we're going to talk a lot about energy transfer in this chapter. Okay, so we're going to say that energy transfers between the system and the surroundings as either heat or as work. Okay, so we're going to represent heat as the letter Q and work as lowercase w. So heat is lowercase q, work is lowercase w. So therefore we can say delta E, the change in energy, is equal to Q plus W. I'm going to say that heat lost by the system must be gained by the surroundings. And if heat is lost by the surroundings, it must be gained by the system. So in other words, we can't just create and destroy heat. It has to go somewhere. In other words, energy has to be transferred somewhere. So I'm not going to create or destroy energy. It has to either be transferred to the system, to the surroundings, or from the surroundings to the system. It's got to be, has to go somewhere, in other words. Okay, so in other words, we can say that the change in the energy of the system is equal to minus change in energy of the surroundings. Okay, so they're just opposites. So we could flip that sign around if we wanted to. Okay, but if it's leaving the system, it must go into the surroundings. If it's leaving the surroundings, it must be going into the system. Okay, we could also say that the energy of the system plus the energy of the surroundings is equal to a constant. And this is your first law of thermodynamics. So this is very, very important not to forget. So if anybody asks you what's the first law of thermodynamics, you should be able to say that, okay, we don't create or destroy energy. In other words, heat leaving the system must go into the surroundings and vice versa. Okay, so one of the biggest challenges with thermo is keeping all of these definitions and variables straight in your mind. Okay, so we've already added, just on this page, 3 variables. So we have heat, represented by lowercase q, work, represented by lowercase w, delta E, which we'll talk about later, is enthalpy, but right now just think about it as terms of energy. Okay, and then we talked about the system and the surroundings on the last slide. So keeping all of these things straight in your mind is one of the toughest things. If you can get that down, the rest, when we get into the math, will be a lot easier. Okay, so try to keep up with all these definitions as best you can. Okay, so if we define work, remember little w, being equal to minus pressure times the change in volume. Okay, if we're assuming that pressure is constant, then we can make this assumption. Okay, so we can define work in this way. So then we can write the formula, the change in energy, delta E, is equal to heat plus work, of course, just like we said before. But now we can sub in for Q, or for W, we can say delta E is now equal to Q minus pressure times the change in volume. Okay, and based on this, we can rearrange the equation and we can solve for heat. So we can say Q is equal to the change in energy plus pressure times volume. Okay, and so by definition, we call this enthalpy. So before I said we were going to put delta E in terms of enthalpy, okay, that's what we're doing now. So delta E is still the change in energy, but now we're going to redefine it. We're going to say, now we're going to talk about enthalpy. So this is represented as capital H. Okay, so we're going to talk a lot about the change in enthalpy in this chapter, thermodynamics. Okay, so delta H we're going to say is equal to heat, which is equal to the change in energy plus the pressure times the volume. Okay, this is the definition. Okay, we're going to look at how to use that and what exactly it means. Okay, so entropy is a state function, just like the other state function we talked about. So representing it with a delta. So delta H is just equal to the final entropy minus the initial entropy. Or in other words, the entropy of the products minus the entropy of the reactants. Okay, so where do we come from? Where do we end up? That's all we care about in a state function. We don't care about how we got there. Okay, and one thing we're going to talk about in this chapter, delta H naught, where the naught is this little kind of degree symbol. Okay, and then we're going to use lowercase f. Okay, so we call this delta H naught of formation. In other words, standard entropy of formation. Anytime you see the little naught symbol, that's going to tell you it's the standard entropy. And if you have the little f, that means of formation. Sometimes you might not see the f represented there, but it kind of means the same thing. Okay, so what is standard entropy of formation? So this is going to be the change in entropy of a reaction that forms 1 mole of a compound from the most stable forms of its constituent elements under standard conditions. In other words, this is going to be the entropy that forms, so the amount of heat that forms, when we take 1 mole of a compound and we form it from the most stable forms of its elements. So if we have something like water, we may say, H2 plus O2 gives us water. Okay, and I'll show you some definitions in the future. Okay, but since we're talking about standard entropy, this will be at standard conditions, of course, 25 degrees C and 1 atm. Okay, so delta H naught F, okay, in other words, the standard entropy of formation for any element in its most stable form is equal to 0. Okay, so what do we mean by that exactly? So if we're talking about something like carbon solid, okay, that's going to be equal to 0. Or if you're talking about something like H2 gas, okay, that's its most stable form, and therefore its entropy of formation is going to be 0. Okay, we're just going to need that definition for later, but just keep that in mind. Okay, so we can calculate delta H naught for a reaction. So before we were talking about formation, now notice we're still talking about standard entropy, but now we're talking about for a reaction. Okay, and we're going to use sigma notation for this. Okay, so we're going to say that delta H naught for the reaction is equal to the total number of moles times the standard entropy of the products minus the total number of moles times their standard entropy for the reactants. Okay, so you're going to take all of the moles, or all of your products, okay, multiply the number of moles times their standard entropy, total those up, and then take all of your reactants, multiply the number of moles of each reactant times its standard entropy, okay, then total those up, and then you're going to subtract the two. Okay, and I'll get more into how to use that sigma notation when it comes time for it. But just keep in mind, that's how we're defining delta H of a reaction. So it's just the total of the entropy of the products minus the total entropy of the reactants. Okay, so let's take a look at two equations here. Okay, so according to the first law of thermodynamics, in any process, we know that energy is neither created nor destroyed. Okay, so we have two reactions here. We have sodium, solid, reacting with chlorine gas. They give us sodium chloride. And we see a delta H value. And in this case, it just so happens that delta H is equal to minus 411.1 kilojoules per mole. We don't really care about the value so much, but notice that the sign is negative. Okay, and then we have sodium chloride breaking into sodium and chlorine. Okay, and they give us a delta H value here. So delta H is equal to a positive 411.1 kilojoules per mole. So notice here we have a positive symbol. Here we have a negative symbol. So equal magnitude, but the opposite sign. Okay, so fine. Neither of these is violating any of our thermodynamic laws. So we have one that's, giving energy off, one that's taking energy in. Okay, but in neither case are we creating or destroying energy. That's great. Okay, so it doesn't violate our laws in any way. So the second reaction actually is not very likely to occur. And if you look at their KEQ values, so this first one we have a KEQ value, our equilibrium constant, much, much greater than 1. Okay, so this, what we're saying is that this first reaction is highly favorable. If we look at the second reaction, we have a KEQ much, much less than 1. So we're saying that the second reaction is not very favorable. And why might that be? Okay, so let's take a look at it. So there must be some factor thermodynamically that drives a reaction. Okay, so we have to have some thermodynamic factor, some energetic factor, okay, that drives a reaction forward. So we can take a look at the boulder on the hill, this analogy. Okay, so we can talk about potential energy, we can talk about kinetic energy here. So what we know is that when the boulder is sitting on top of the hill, we know we have a high degree of potential energy. So if we again define potential energy equal to the mass times the height times gravity, or mgh. You could put those two are the other way around. Matter of fact, let's do that. So mass times gravity times height. Okay, so what we have here, so we have a boulder that has a lot of mass, or maybe a little mass, but let's say it has a lot of mass. Okay, we have some gravity. If we're on Earth, we assume gravity is pretty strong. Okay, at least to us. Okay, then we have some height. Okay, so we have some value here, h. Okay, so what's going to happen if we come to the top of the hill and we push the boulder in this direction? We know that it's pretty easily going to start rolling down the hill. Okay, it's going to continue on. And so what's happening here? So the height is gradually decreasing. So our potential energy is slowly going away. But what else is happening? So we're gradually converting that potential energy into kinetic energy. Okay, so as it moves down the hill, it's gaining energy. Okay, so it's losing potential energy and it's gaining energy until eventually it's maybe down here somewhere. Okay. So now that's at the bottom of the hill. It's released all its potential energy. Now maybe we have something that stops it. Maybe we have a wall, okay, and it releases all that kinetic energy into some blocker, whatever it is. Okay, so now what we have is we have a boulder at the bottom of the hill. So what happens now if we want to maybe roll the ball back up the hill? It would take a lot of work, right? So it was easy to push the ball down the hill, but it takes a lot of work to push the ball back up the hill. Okay, so that's sort of what we're talking about here only in terms of reaction. So if we go back a slide, so here we're talking about this first one. So we're releasing energy. Okay, so that would be like pushing the ball down the hill. Okay, and then the second one, this would be a representation of pushing the ball back up the hill. Okay, so it's not energetically favored, in other words. So the first one is highly energetically favored, whereas the second version, maybe not so much, and it's going to take a lot more energy. Okay, so in other words, this gives us directionality. Okay, so what do I mean by directionality? Meaning that the reaction is very favorable in one direction, not so favorable in the other direction. In other words, it's easy to roll the ball down the hill, not so easy to push it back up. The same is true with chemical reactions. Okay, so let's talk about this in terms of energy over time. Or in this case, we're going to talk about chemical potential. Okay, so here we have chemical potential on our y-axis, and we have the extent of the reaction on our x. Okay, so let's look what happens. So the first reaction we have here. So we have, again, sodium combining with chlorine to give us sodium chloride. Remember our KEQ, our equilibrium constant, it's much, much bigger than 1, meaning this is highly favored. Let's take a look at how the reaction proceeds. Okay, so we start from some high chemical potential, and as the reaction goes forward, okay, we move to some low chemical potential. In other words, the energy of the system is going down. So if we move from reactants to pure products, we're going down in energy. So in all of thermodynamics and all of chemistry, at least as far as I know, all reactions that are energetically favored, in other words, energetically downhill, those are going to proceed rather easily, or at least they'll be favorable. Okay, so that may not always be completely true. Okay, but generally speaking, if we go from a high energy to a low energy, that's generally speaking going to be energetically favorable. Okay, so let's look at the other one. So here, this is the example of the easy reaction, the one that will proceed. Let's look at our second reaction here. Okay, so now we have the reverse reaction, where we have sodium chloride breaking into sodium and chlorine. And remember our equilibrium constant, much, much less than 1. So this is a very unfavorable reaction. So let's look at how it might proceed. Okay, so now our reactants are sodium chloride, our products are sodium and chlorine. Okay, so notice this time, we're going uphill. Okay, so we're starting from some low energy, and we're going to some high energy. Okay, so in other words, it's not energetically favored. Okay, so in order for this reaction to proceed, we have to push the boulder back up the hill. Okay, that's not very favorable. And in terms of chemicals, we're going to have to put some energy in. We're going to have to help it fight to get up this hill if we want it to proceed. So that would be an example of a reaction that wouldn't just proceed on its own. Whereas the top reaction probably would. I mean, it's very energetically favored. So if we just put these things together, probably we're going to get this reaction to occur. Okay, so what if we look at a reaction that's at equilibrium? Okay, so now we have hydrogen combining with iodine to give us 2Hi, and we have some equilibrium constant around 56. Okay, fine. Okay, so just some sort of middle of the road equilibrium constant. Okay, so we have an equilibrium though here. Okay, so same kind of graph, chemical potential, in other words, energy, pure reactants going to pure products. So let's look what happens. Okay, so in this case, we have sort of a middle point here, where the reaction is favorable in neither direction. So if we start from up here, okay, if we're moving this way, okay, the reaction is favorable, continues to be favorable, until we get to some point. So until we get to here. Okay, now if we wanted to go continue on towards our products this way, okay, now we're going to have to increase in energy again. So it was energetically favorable, so we're moving down the hill. Okay, but once we get to this point, okay, it's no longer going to be energetically favorable. Now we have to increase our energy again in order to keep proceeding. Okay, so in the reverse direction as well. So remember, with the equilibrium reaction, we have a forward direction and a reverse direction. So now let's talk about the reverse direction. So it's a similar thing. Okay, so if we want to continue in this direction, keep going. Okay, it's going to be energetically favorable, again, until we get to this point. Okay, so we end up with sort of a situation where we have the boulder stuck in the middle. So you can kind of imagine putting a boulder here or putting a boulder here. Okay, and they're going to roll down until they get to this valley. Okay, and once they have no more energy left, they're going to kind of be stuck in the valley. The only way to get them out would be to apply energy. Okay, so this is our equilibrium reaction. So along the course of the reaction, they reach some energetic point that's energetically favorable. Okay, and then, in other words, it gets to a point where it's not energetically favorable for it to proceed in the forward direction or any further in the reverse direction. So it's just going to kind of stay at that equilibrium. Okay, so hopefully the boulder analogy kind of helps a little bit. Okay, but this represents an equilibrium reaction. Okay, so just expanding on that a little bit further, we could have some reactants at some energy. We could have products at some energy. Okay, then our equilibrium mixture is going to reach some low energy point. Okay, so if we think about the y-axis in terms of energy, okay, over the course of the reaction, we're going to get to this valley. Okay, where basically the energy is the most favorable for the reaction. Let's put it that way. Okay, so it's not favorable to go in the reverse direction. It's not favorable to go in the forward direction either. Okay, so that would be over the course of the reaction. Okay, then on the right, we kind of have that same thing in terms of the boulder again. Okay, so as it rolls down the hill, it gets to some point where it's not favorable to keep rolling in the forward direction or to roll back up the hill. Okay, so that's kind of a good intro to thermodynamics. Hopefully some of that was a bit of a reminder if you've taken physics. In this next section, we'll talk about spontaneity. So what is a spontaneous process and what isn't? Okay, so the first thing we'll look at is just an analogy. And we'll talk about, first let's define what a spontaneous process is. Okay, so a spontaneous process is a process that is capable of proceeding in a given direction without needing to be driven by an outside source of energy. Okay, so it's a process that will just naturally occur. So first let's look at an analogy. So here we have two glass bulbs. Okay, and we have one that is full of a gas, and we have the other that's under vacuum. Okay, then we have them separated by a valve. Okay, so we have the two bulbs blocked from each other with a valve. So what's going to happen if we were to open this valve? And you can probably already picture in your mind what's going to happen. Okay, so if we open this valve, remember we have vacuum over here, we have a gas on the other. So you can probably imagine that the gas is going to flow through the valve into the evacuated bulb. and you would be right. Okay, and that's what's known as a spontaneous process. Okay, so the idea of the gas moving through the valve into the evacuated chamber, that's a spontaneous process. It's going to happen without you having to apply anything. Okay, so you just open the valve and it's going to apply. Okay, so that's a spontaneous process. Now, what would be a non-spontaneous process? So a non-spontaneous process is a process that can only occur with some outside intervention. In other words, the surroundings have to do some work on the system. Okay, so the surroundings have to do some work on the system in a non-spontaneous process. Okay, whereas in a spontaneous process, it just occurred on its own. The surroundings didn't have to intervene in any way. Okay, so here we have a non-spontaneous process, and you see the reverse arrow. In other words, taking the gas and putting it all back into the first chamber, probably not going to be so easy, right? Okay, so that would be a non-spontaneous process. Okay, so a spontaneous process doesn't necessarily mean that it's a quick process. Okay, so here's the example of some some wheels, the inner part of the tire, the metal part, that's rusting. Okay, so rusting, if you were to just leave some metal outside, generally speaking, we know that eventually over time, rust is going to occur. Doesn't necessarily mean that it's quick though. I mean, it takes time for rust to build up. We all know this. Okay, so all that means is that it's favorable though. Okay, so we go from some reactants to some products, and over time we can go through some transition state. Okay, we end up with, in this case, we end up with maybe aluminum oxide, something like that. Maybe these are aluminum wheels. Okay, and they end up with aluminum oxide. So even though it's a spontaneous process, doesn't mean that it occurs quickly. Okay, so it could occur quickly, but in this case, that's what we're talking about. Is it doesn't necessarily occur quickly. Okay, so in this case, we have to go through some transition state that may take some energy, some time, some chemical energy to go overcome that energy state, and then you'll move on to the more energetically favorable product state. Okay, so in this case, they give us a note that says a spontaneous reaction occurs slowly if it has a high activation energy. In other words, it has to work to get first over this hump, and then it proceeds rather easily. Okay, so that would be your EA, or your activation energy. A spontaneous process will always move a system towards equilibrium. Okay, in other words, it again has directionality. A non-spontaneous process will always move a system away from equilibrium. In other words, it also has directionality. So if we look at spontaneous process first, okay, so since we know that it's energetically favorable to move towards our equilibrium state, that means these are going to be spontaneous from both the reactants and from the products. So we call that the spontaneous direction. Okay, but we're talking about a non-spontaneous, in other words, the non-spontaneous direction moving away from equilibrium. Okay, this is always going to take energy. Okay, so I'm going to have to put energy in to move away from equilibrium. So that would be an example of a non-spontaneous reaction, or non-spontaneous system. Or I shouldn't say system, I should say process, a non-spontaneous process. Okay, so a true reversibility can only occur at equilibrium. All other points in the curve are viewed as irreversible. Okay, so some spontaneous processes are temperature dependent. Okay, so for instance, if we have a flask of water, okay, and we put it in conditions where we have a temperature. So let's think about this direction first. Okay, so we have a glass of water, okay, or a flask of water in this case, and we put it in temperatures. We have a temperature less than 0 degrees C. In other words, below the freezing point of the liquid, of the water in this case. Okay, so below 0 degrees C. So without me doing anything, or without you doing anything, the water will naturally just freeze. Okay, so this is a spontaneous process. So at temperatures below 0 degrees C, water naturally freezes. Okay, so this is a spontaneous process. We don't have to do anything. It just happens. So if you take a glass of water and you put it in your freezer at home, you'll see this. And you don't have to come check on it. You don't have to do anything. Okay, it would just freeze all on its own. Then if you take that same frozen glass, or that same flask with ice in it, and you put it in temperatures above 0 degrees C, it's spontaneously going to turn back into a liquid. Okay, so we've gone from solid ice to back to liquid water without us having to really intervene. All we did was change the temperature. Okay, we just changed the environment, but we didn't actually really do anything there. We just changed the environment. Okay, those are examples of spontaneous processes. Okay, so this is the last little section I really want to cover with this first sort of intro video. Okay, so I just want to get into the second law of thermodynamics and kind of give you a good idea, kind of a good foundation on where we're moving towards. Okay, so let's start out from just entropy. Where did it come from? Okay, so around 1824, a French scientist, his name was Carnot, he's probably heard of the Carnot cycle, that's what we're going to talk about here, published his findings from research of steam engines. Okay, he was concerned with the heat to work efficiencies of steam engines. So back then, they were working with steam engines, so they wanted to study the efficiency of these steam engines. Okay, so he was wondering, was the work available from a heat source unlimited? And could the efficiency of a steam engine be improved? Okay, so through his research, he developed the ideal heat engine. It's known as what's called the Carnot cycle. Okay, so he said the efficiency of the ideal engine was dependent only on the temperature of the hot and cold reservoirs of the engine, not on the substances, in this case steam, that drive the engine. Okay, so he was only concerned with the hot and the cold reservoirs of the engine. Okay, so he was saying it has nothing to do with the actual substance driving the engine, just the temperature of the hot and cold reservoirs. So, in other words, how likely was heat to flow through this engine? Okay, so later on, about 1864, we have Clausius. He published his research expanding on the Carnot cycle. So he said specifically he was interested in the distribution of heat within the Carnot's ideal engine. So he coined the term entropy to represent dispersal, important word there, dispersal of energy in the system. Okay, so it has since been expanded to represent dispersal of both energy and matter in a system. But originally he was just talking about heat. Okay, but we defined entropy as a state function. So we define this as delta S, capital S for entropy. So delta S is just the change in entropy. So again, it's a state function. So all we care about is the final and the initial. Where do we end up and where do we come from? So it's a state function. Okay, so we're going to define that as delta S, or in other words, the change in entropy. Okay, so here we're going to say that entropy is an abstract concept. Okay, so energy, in other words, is the dispersal of energy. It's quite different than energy itself. So there's two terms here, enthalpy and entropy. Very close, but they're very different. Okay, so entropy is just the dispersal of energy. It's not energy itself. Okay, so energy can either created nor destroyed. We know that. So however, when energy is dispersed, entropy is created. So we can create entropy. So it's an abstract construct. It can be created and destroyed. So we can raise and lower entropy as we wish. Okay, so therefore, entropy can be created. Okay, so he famously noted that heat cannot spontaneously flow from a colder object to a hotter object. Instead, energy in a hotter object will be dispersed into a colder object. Okay, so heat will move from a hotter object to a colder object, and it will be dispersed into the colder object. In other words, it's not necessarily transferring, it's being dispersed into. Okay, so this represents an increase in entropy. This means that a spontaneous processes result in the dispersal of matter or energy, and therefore an increase in entropy. Okay, this leads us to our second law. Okay, so that's important to note there also. Okay, so we're going to move heat from the hotter object to the colder object. I think we've talked about this before, but remember that the cold object doesn't really cool the hot object, more so that the hot object disperses its heat into the colder object. Okay, so let's look at the second law. Okay, so with the understanding that the universe is equal to the system and the surroundings, so going back to our analogy of the beaker, okay, so you have the beaker, that's our system. So if we measure the temperature of the water inside the beaker, and then we have something like a hot plate, that's the surroundings, and the universe, including the lab and everything else, so the system and the surroundings are all within the lab, which is all within the universe. Okay, so everything outside of the system and the surroundings, they're both inside of the universe. or I should not say anything outside the surroundings, but the system and the surroundings are both inside of the universe. Okay, so now we can state the second law. Okay, so we can say that for any spontaneous, in other words, irreversible process, the entropy of the universe is always increasing. Okay, so we can say delta S, in other words, delta S of the system plus delta S of the surroundings must always be greater than 0. Okay, so it must always be higher than 0. It must always be increasing. Okay, for any process at equilibrium, reversible, the entropy of the universe is unchanged. Okay, so for equilibrium, we have delta S of the universe equal to delta S of the surroundings plus delta S of the system, okay, equal to 0. In other words, it's just not changing. So notice we're talking about delta here, so that might sound a little bit confusing. Okay, but here we're talking about change in entropy of the universe. Here we're talking about also change in the entropy of the universe. So what they're saying is the change of entropy for equilibrium is unchanged. Change in entropy of a spontaneous process must be bigger than 0. Okay, so remember that delta means change in. Okay, and a decreases in entropy for the universe, in other words, delta S of the universe less than 0, are not allowed. We would call this an unallowed process. Okay, so don't forget your second law. Okay, so in other words, entropy always has to be increasing. Entropy at equilibrium, change in equilibrium, entropy at equilibrium is equal to 0. Okay, and a decrease in entropy of the universe is never allowed. Notice of the universe here. I didn't say a change in entropy was never allowed. No, change in entropy of the universe is never allowed. So what exactly do I mean by that? Okay, so we can lower the entropy of the system. Okay, so for instance, the non-spontaneous processes may have a delta S of the system less than 0. They are allowed as long as delta S of the universe is still increasing. So I can lower the entropy of the system as long as overall my entropy of the universe is increasing. Okay, so I can say delta S universe is equal to delta S of the system plus delta S of the surroundings. So in other words, what am I saying here? So as one goes up, the other has to go down, or as one goes down, the other has to go up. Okay, so I don't necessarily have to have a decrease, but I should always be increasing overall. Okay, so not necessarily that one goes down, one has to go up, or that is true. So if one goes down, one does have to go up, but they could also both be increasing. That's what I'm trying to say. So they could both be increasing, but if one does go down, so for instance here, we're lowering the entropy of the system, so we have to increase entropy of the surroundings. So therefore, the net increase or decrease is an overall increase of the universe, entropy of the universe. Okay, hopefully that wasn't too confusing. All we're trying to say there is that overall, the entropy of the universe has to be increasing. Okay, so currently you can kind of define entropy as being a measure of randomness. That's one way to look at it. Okay, so hopefully this might help put it more in perspective. So a measure of chaos or disorder. Okay, that's kind of how we've defined it more modernly. Okay, but just remember, so in this case we have, we would say a low energy or low entropy, I should say, not energy, entropy. So low entropy. So we have red jelly beans and we have white jelly beans inside of a beaker. Okay, and they're nicely sorted. So we have all the red beans on one part, all the white jelly beans on the other part. Okay, so this would be low entropy. So what happens then if we take something like a glass stirring rod and we're to stir up the jelly beans? So now they're sort of all over the place. So there's no order at all. So that would represent high entropy. Okay, so I think that's a good place to stop for today. So we're at about 40 minutes or so. Hopefully that gives you a good background on thermodynamics. So we've covered some more of our definitions. So now when we come back, we will talk more about the finer details and start to put some of those ideas into play. Okay, so I'll see you next time.